Welcome everybody on Zoom. Welcome everybody in the lecture hall. Welcome everybody from the future. Today we are going to finish what we started on document stores. There's actually not so much left that we have to discuss. It's basically just indices. And then we'll continue with JSONic, the language to query denormalized data sets. So you remember that a document store is, instead of relational tables, it's based on data that is shaped as collections of trees. You know that collections of trees are a denormalized version of relational tables. It's what happens when you drop all of the constraints like atomic integrity, relational integrity, and domain integrity, meaning that you can really have a collection that is a huge mess with trees that have nothing to do with each other, but you can, and actually should, often have some schema where the trees then look alike and respect the schema. But this is something you are not obligated to do. So you can also just have heterogeneous collections, right? So it looks a little bit like this. So you see it's a bit heterogeneous. And you really need to keep in mind that we are talking about a huge number of small objects, really billions, trillions of objects, of documents. But the size of a document can no longer be higher than 10 megabytes or 16 megabytes for MongoDB. So this is the kind of the size that you constrain. Okay, so you will not have a collection, for example, with 10 objects that each have 1 gigabyte. No, that doesn't work. That's not what document stores do. All right, and we saw two kinds of indices. And indices are here to accelerate the queries. This is something you cannot do with Spark or on top of a data lake, right? If you are using Spark and you need to find specific objects in there with a filter transformation, you have to scan the entire data, right? So it's not going to be instant. However, in the case of document stores, just like relational database systems, you can get an object from a collection of trillions in just 2 milliseconds. Very, very quick. And the reason for this is that unlike a data lake, you don't just store JSON files or Parquet files and so on. Instead, you import the data into the document store, and then the document store stores the data in any way it wants, right? It's proprietary. So in the case of MongoDB, it's using BSON. And because the system stores the data in any way it wants, then it can also create indices to make the lookups faster. And this is why we are able in that case, because it's based on importing data to build indices. So the first index we have is a hash index. It's very good at queries that select specific values. So it's typically where you have a where clause with an equality. So hash indices are extremely good at that. What's the complexity of a lookup with a hash index, assuming no collisions? O of 1, exactly. So that's the first kind of index. But it doesn't support range queries, which is why we have a second kind of index called the B plus trees. And these actually support range queries, but the complexity is not O of 1, it's O of, again, you're awesome, perfect. So these are the B plus trees. Now, concretely, the way that you can create these indices in MongoDB is with a command on the shell, or you can also do it in a host language. And in JavaScript, it's a function called createIndex. Then you specify what you want to index. By the way, here it's even a nested key that you index, which is totally fine. There is a dot. And so you ask MongoDB to create a hash index on this. You might remember that I told you you can either ask for blocking everything until the index is built. Then it goes 100% CPU on building the index. Or you ask for the index to be built in the background, meaning you can continue to use MongoDB, but it's going to be a bit slower until the index is built. And then you pay another cost when you insert new data or modify the data. It's slightly slower because you not only need to modify the data, you also need to update the index every time. All right, but once you have the index and you go ahead and query using some field here that is complementary, that is matching an index. You might have 5 or 6 indices. MongoDB is going to try to come up with execution strategies with the index, without the index, with this index rather than that other index. Sometimes you might have several indexes in competition. And then it calculates the costs, and then it selects the query plan that it thinks is going to be the best, and then it goes ahead and executes it, right? So it's good to think in your head, if you see a query, is it going to be supported by the index? In that case, yes, because the field here is the same, and we can directly query from the index the exact records that we want to return, records, documents. Okay. Then, so this is done with hash, right? Then you have the B+3 indices, for which you specify the keys. It can be several of them. For a B+3, you can have several keys. That's called the compound index. And you can specify that in that case, its birth is ascending because of the 1, and death is -1, so it's descending, right? So the idea is that it's lexicographical. You first sort by birth ascending, and for the same birth, you sort by death descending. Note that there is something that I don't quite like. It's the fact that the order of the keys here in the API is important. There is the first one and then the second one. The reason I don't like that is that normally in JSON, the order is not supposed to matter. So that kind of breaks a little bit the idea, but this is how it is, right? So this is how the API is configured, and somehow it does see an order of the keys there, right? But you really have to consider that a breach of the semantics of an object, but that's how it is. Yes, there is a question.
How should I look at creating indices from the perspective of data independence? I can tell if it is a breach of data independence or not.
Ah, okay, yeah, that's a very interesting question. So let me put it this way. In the beautiful world in which data independence applies 100%, you don't have to create indices because the system will do it for you, right? So this is the ideal database system that's going to do it. In fact, there exist products on the market that learn from the way you use the database and automatically figure out which indices to build. That actually exists, right? MongoDB is not quite there yet. So this is why, in that case, you do need to help a little bit the system by specifying the indices you want, right? So it's kind of the difference between the ideal world and the real world, right? So in the real world, most of the systems need a bit of your help in order to know which indices you build. Does it answer the question? Right? Awesome. Okay, in fact, this is why knowing a little bit about how a system works makes it easier for you to figure out how to write the queries. Again, ideally, you shouldn't have to bother about how you write the query. It should anyway be fast. But in real life, knowing how it works will help you writing the queries in a way that, that will work better. Okay, all right, now, I would like to continue where I left off last time, where I have a compound index with B+3s. Here I have the birth and death, so I have two keys here, and here I'm using the first one of the two, right? This actually will work, because if you think of the compound value, like the list of all compound value ordered lexicographically, first sorted by this and then by that, if you look at all of the births that are after or including 1980, if you look at the pairs, birth date, birth, death, ordered lexicographically, this is an interval, right? These are all the pairs, birth, death, such that the birth is greater than or equal 1980, right? So since it's an interval on the pairs, you can use the range even though there's only the first key, right? However, it does not work if you take the second key. Because if you look now at a range of deaf years or some interval of deaf years, since it's the second key, the places where you find a famous person who died in 1887, there will be one for maybe every possible birth date. So there will be one here, and then one here, and then one here, and then one here, but it's not an interval, right? Who sees that? Right? It's not an interval anymore because it's not the first key. So that only works that you can use the index if this is a prefix of the number of keys, right? A prefix of the list, the ordered list of keys. So birth would work here and not this. In that case, you just don't use the index. You just directly go ahead and do it with a full scan. All right. So concretely, what that means is that whenever you have a compound index with multiple keys, again, in a specific order, because of the little breach of JSON object semantics, there is this order, then it's as if this index also existed. So you can also build queries that use just the first key, or queries that use the first two, right? Or all three. But it has to do like this, 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 and not this, not this, not this. It has to be a prefix, right? And then it works. Why is that important to know? Because many people do that mistake. They will actually, so when you want your website to use MongoDB and you want to often execute the same kind of queries and you build indices to make them efficient, some people make the mistake of creating, for example, this index and also created that index. But this is a waste of space and a waste of time, because you don't need to build this index in addition to that one, because that one already gives you that for free, right? So you need to know that. That will save you a lot of costs and a lot of space to actually be aware of that. Now creating the index, which index to build is really based on your use case. You really need to sit and think about what are the common queries that your database is going to be receiving. And then you think about the index that you create.
You have a question?
Yes.
Is there a difference between ascending and descending indices in practice?
No, it's really because of the impact that it has at query time. For example, if you, let's say, if you have here a birth and then death decreasing, that allows you to access them in a certain order. Like in some cases, if you want to order at runtime in a specific order, and that order matches the order of the index, then you can just look at the records directly in the right order. It's that kind of benefits that you get. And it also affects the intervals, because then you within the same birth, the second key will be ordered in a different way, right? So it really depends on the query that you're looking at, that in some cases it makes a difference, right? Did it answer the question? Yeah, awesome. What I should add is new features that actually didn't exist before, but now MongoDB allows you to mix hash indices with B+3 indices in the same index. This is new, but not in any way you want. What MongoDB allows you now is to have one key that is hashed, one that is hashed, and all of the others are 1 or -1. It's kind of a hybrid index between hash index and B+3, but you can have at most one key with the hash keyword like this, and all others must have 1 or -1, right? This is new, and again, at every release of MongoDB, they keep improving the system. Who knows, maybe in the future, they will provide a way to have multiple keys that are hashed. You know, you never know the direction in which it goes. It basically depends on the customers and what people ask or what people need, right? Okay, what else can I say? Yes, the indices, if you have an index, you can also use that index for the shards, meaning that once you have the index, you can ask MongoDB to shard the data following the index that you just built, right? What happens by default is that you have an index on this object ID, the _ID field. It always exists in every object. By default, MongoDB builds a B+3 index on this field. And by default, MongoDB is going to shard based on the object ID intervals, right? This is the default, but you can change that. You can also reorganize the shards based on a different key than just the object ID and get more control, right? The idea is that the more advanced your knowledge of the system is, the more you can fine-tune it and make it do what you want and much faster. All right, that was actually the last slide of MongoDB. Do we have any questions before I move on? Okay, no questions. Some last words, just so that you are not surprised. If you try to Google around the documentation for the API, do not be surprised if sometimes you might find something that looks different. It's because I showed you the JavaScript API right here, but there is also a Python API. And the Python API doesn't quite look like the same, right? So don't be surprised, there's multiple APIs. But on exam day, we don't have an implementation on MongoDB, so you're not expected to program. It's just going to be questions in the Moodle. We might show you queries and ask questions about that. But this is all based on the JavaScript API that I'm showing you here. All right, and maybe there's even one in C++, in Java, so there's many languages. And in fact, this idea of having some query API or query language close to the database, and then an additional layer with a programming language, an imperative language, it's called the host language in that case, is very common, right? So you have a host language, and then you have the nested query API or query language inside, right? So host languages can be Java, C++, Python, R, and so on, Python. And query languages can be SQL, can be the Spark RDD API, the Spark Data Frame API, can be the MongoDB API, or Spark SQL, like SQL, JSONic, and so on. Okay, so let me stop here, this part of the course, and then I move on to querying the normalized data sets. We have a question, yes?
How is the hash function chosen?
This is internal, this is done by MongoDB. So choosing a good hash function is out of scope of that course. I think you might find maybe theory about that in cryptography lectures, because hash functions are core to cryptography. But in the case of MongoDB, you don't have to worry about that. It's just going to pick a hash for you. It might be that you can tweak it, by the way. Yes? Mm-hmm. So the question that I'm repeating is about how do you know how many indices you should create and which indices you should create. This is based on the queries that you expect. You might also change it over time. You might try with a specific set of indices, and then you notice that some queries are slow, so you add other indices and so on. I can tell you a bit of the thoughts behind that, a bit of the practical thinking. What restricts the number of indices you could have, because you're absolutely right that you could have just all of them or create 100 indices, right? The first restriction you have is space, because the disk capacity, the index is going to go on disk, right? And you are limited on the space you have on disk. Every time you create an index, it eats more of the disk space. So at some point, you have a hard constraint on the indexes that you can actually build. You also have a constraint on the speeds, that the more indices you have, it's slowing down the system. But I think the space constraint is usually the first, the biggest constraint that you have. And the fact that you have a constraint on the number of indices you can build forces you to make a choice. And the choice is really a call based on what are the most often used query patterns that you expect. Now, what's going to happen very often is that the queries that you are going to receive against your MongoDB collection, they don't come directly from the users. It's not the users that directly create their queries and you could get anything. Usually the queries that you get are written by you or the same team or people in the same company by Java or Python or the host language. So you know what kind of query patterns you have in the host language. And based on that, you can think of what indices you should use based on how often they are called, right? There is another important factor to consider for the indices. It's that in general, what's going to happen is that you might have, let's say, 5 or 6 indices, and maybe there is enough working memory, RAM, for one of two indices. So you might be able to promote 2 indices to be fully in memory, but not all of them. So you're going to have some in memory and some you have to use from disk. Or you can only get into the memory the upper levels of the B+3, and then the lower levels are on disk. But when you manage to create an index that fully fits in memory, this is a big performance improvement, because then you don't even have to read from disk. So this is even much faster. And you can also control which ones you get in memory. And so sometimes it's good to sit down and calculate, maybe in theory, like what's your expected size of the index? Does it fit in memory? Do I fit 2 indices in memory? Then you can also verify and ask MongoDB after it built the index, it will tell you the size it has. And so here it's part of the whole optimization that you're making on which indices to build. It also includes how many of them will fit in memory and which of them do you want to fit in memory. Right? Did it kind of answer your question? Yeah, awesome. All right. So let me move on then.